All right, so we were talking about graphing and v equals d over t and stuff like that the other day, okay? So I want to go over just a few kind of word problems that have to do with graphing, just so you can see how they're kind of worded, and also expose you to a few different types of graphing questions so that you kind of understand what they're looking for, different situations that can come up. All right, so in this first example, what we're really focused on here is what the slope represents in a position versus time graph. Okay, so at the end of the school day, student A and B say goodbye and head in opposite directions, walking at constant rates. Student B heads west to the bus stop while student A walks east to her house. After 3 minutes, student A is 300 meters east and student B is 450 meters west. So for graphing that, okay, on a position versus time graph, it's going to look like this. Okay, and we're going to have, okay, this person here is ending up 350 meters east, okay, and this one is ending up 450 meters, or sorry, 400 meters west, right? So who went further? Student A or student B? Who went further? Student B. Who went faster? Student B. Has to be because same amount of time, right? It was 3 minutes. They both walked for 3 minutes. One of them ended 350 meters, one of them ended up 400 meters. Or, sorry, I have it wrong. 300 meters and 450 meters. Okay, so one of them walked further in the same amount of time. That's why their line is steeper than the other one. Okay, they went further in the same amount of time, right? So all we're trying to illustrate there is that the slope of that line represents their not just speed, but on this graph also velocity, right? Because it's showing their vector, right? It's showing that one of them went west and one of them went east, okay? So it's showing how fast they're going and in what direction. Okay. Right, so on this question here, we got a wildlife biologist measures how long it takes 4 animals to cover a displacement of 200 meters. I have no idea how they run an experiment like this. Last time I checked, you're not getting wild animals to run 200 meters on the track, okay? This has got to be not a very controlled experiment, different landscapes and terrain and stuff like that. All right, so what they've got is that an elk takes 10.0 seconds to run 200 meters. To give you an idea, the world record is somewhere like in the high 18s for humans. So you're not going to outrun an elk. Ever. Okay. Coyote, 10.4, also pretty fast. Okay. Grizzly bear, and this is a slow grizzly bear, 18 seconds. All right. So all of you people out there who think that well, I just run away from a grizzly bear. Remember this: a grizzly bear can run faster than an Olympic athlete, even a slow one. A slow grizzly bear, not a slow Olympic athlete. Okay. A slow grizzly bear. And here's the other thing: they can do that in the forest. Okay, you're running through the forest, you have to bob and weave and move around trees. Grizzly bears knock them down. Okay, they run in a straight line, break off like trees that are this big around. Okay, they just snap off on their shoulders while they run, doesn't even slow them down. All right, so if you think you're going to outrun a bear, the only way that's going to happen is if you mess yourself and they slip in it. Okay, and even then they'll probably still get up and catch you. Which, I don't know, maybe you'd be so embarrassed after you'd want that. I don't know, but, okay, grizzly bears are really fast. You're not going to outrun them. Okay, and then a moose, 12.9. So all of these animals are pretty fast. Okay, if we put them all on a graph, okay, which one of these lines, okay, and we'll just say A, B, C, and D, which one of those lines represents the grizzly bear? D. Okay, grizzly bear was the slowest of those animals. All right, so it took 18 seconds for them to go the 200 meters. Right, then this would have been the moose, and this would have been the coyote, and this would have been the elk. All right, so we'll go over that. So we see the lines steeper and steeper and steeper. Faster they're going, steeper the slope of the line. Okay. All right. What kind of motion is being shown on that position versus time graph? Yep. This object is accelerating. Okay? And when I say accelerate, I don't mean it's going faster. In fact, this one is going slower. Right? And we know that because the curve is getting less and less steep, where it's getting more flatter, more flatter. It's getting flatter and flatter as it goes along, right? Because this object is coming to a stop. It's coming up to a river, okay? So it's slowing down, right, and flattening the curve. Everybody all right with that idea? So these are the kind of things I would ask you on a quiz or on a multiple choice question on a test. Here's a position time graph. A, B, C, or D applies to what you see here, right? So your options on a graph like that would have been object is speeding up, object is slowing down, object is traveling at a constant velocity, object is not moving, okay, or something like that. You have to pick the correct answer by recognizing, all right, this is a position time graph, it's a curve, so it's neither of the other two, okay, is it speeding up or slowing down? That kind of thing. Okay. So this is a velocity versus time graph right here, okay? And we're seeing, okay, a line that's going diagonally upwards. What would a position versus time graph of that look like?
Just be a horizontal line?
Nope, not a position versus time graph. No. Okay, what does it mean? What is that graph saying? It's a velocity versus time graph. What is it saying the object's doing? Speeding up. All right, what does speeding up look like on a position time graph?
Like curves upwards?
Curves upwards, exactly. Our position versus time graph would look like this, okay? Showing an object going faster and faster. Okay, you got it backwards. If that was a position time graph, the velocity time graph would have been a flat line. I think that's what you're thinking because we did that yesterday. Okay, and then for this one here, it says calculate the acceleration using the graph below. All right, in Science 10, we learned this formula, A equals VF minus VI over T. Would I be able to get those three pieces of information from this graph?
Yep.
Yep, it's a velocity versus time graph. Okay, what's my final velocity? 0. My initial velocity is 10, and this takes 10 seconds. Seems like my acceleration would be -1 meter per second squared, because I would have 0 minus 10 over 10. Okay? That would be -1 meter per second squared, slowing down by 1 meter per second every second. Okay? Did I also just calculate the slope of that line? Definitely. Okay? Remember that this is okay, y minus b over x. Okay, this was b, this was y, that was x. Okay, you're right with that. Okay, I want you guys to try that one. I want you to calculate from that velocity versus time graph the total displacement and the average acceleration over the whole trip. See what you remember from yesterday. So when we have a velocity versus time graph, okay, we want to calculate the displacement. We need to look at what's going on in each section of the graph. So in this first section of the graph, for the first 4 minutes, okay, and actually we're just going to change this to seconds. How many people realized it was in minutes? Okay, did you do the calculations in minutes? Okay, so we're just going to say it's in seconds because I don't know why someone would use minutes on this. We're just going to do this way. Okay, all right, so we got the first 4 seconds of this motion. The object is traveling at a constant velocity of 3 meters per second. So if I want to calculate displacement, okay, during that part, I just take my average velocity and multiply by time, right? V equals d over t. And so I'm going to have 3 meters per second times 4 seconds, and this is 12 meters. So that part's pretty straightforward. Okay, and it's 12 meters east, according to the graph. Now, during the next second, what's the object doing? It's slowing down. Okay, so if it's slowing down, okay, then I have to take into account that its average velocity is halfway between its top and bottom. Okay? So what I'm going to do is have this box down here represent how far it would go if it traveled at this final velocity for the last 4 seconds, because essentially it's, or sorry, last 6 seconds, because that's what it's essentially doing, plus how far it travels while it's slowing down. That would be this triangle here. Right, so if I'm looking at this triangle says that the change in velocity goes from 3 to 1. Okay, so the height of this triangle is 2. Okay, and the base of this triangle is 1 second. Okay, everyone with me on that? Okay, so I'm just going to figure out then what the area essentially of this triangle is. Okay, so base times height over 2, so the base is 1, the height is 2. That's 2 divided by 2 is 1. Okay, so we got 1 meter there. Okay, and then we've got this last bit here, okay, to calculate average velocity of 1 meter per second for 6 seconds. So, meters. So we're looking at 19 meters in total. So the total displacement is 19 meters east. Okay? That's a very typical question like you would have got in Science 10. Okay? Also a very typical quiz question, possibly tomorrow. Like you definitely have a quiz tomorrow, maybe something like that will be on it. All right, the second part of this question wanted to know the average acceleration over the whole trip. Well, we just used that formula on the last slide, VF minus VI, okay, over T. So VF is 1, VI is 3, and that takes 10 seconds. So we're going to have 2 over 10, so our acceleration will be negative 0.2 meters per second squared. Questions on that one? All right, so these ones here would be much easier, okay, for calculating displacement. Obviously, this is just a box, so it's just going to be, you know, the average velocity of 2.2 times 10 seconds will be 22. This is just, okay, finding our average, which is halfway up, okay, multiplying it by the base. All right, we've done lots like that, so we're just going to skip those. But this one, okay, is a really good question. So in the situation they tell us here is a bird starts flying south. Its motion is described in the velocity time graph in figure 1.6. So that's this graph here. Okay, so this is a graph of a bird, and it's its velocity versus time graph. Okay, so I want you guys to do those 3 questions, A, B, and C. Right? Part B involves a little bit of calculating. You have to calculate some accelerations using that formula we just used. Yes, that's this one. Right, but the rest of it is just analyzing the graph. Okay, not even having to do any calculations. Right. So give you a few minutes on that, and then we'll walk it through. C is like the big deal on this question. It's the one I want to go over the most because it's the one most people get wrong. Okay, when we're analyzing the graph. Give you a few minutes on that, and we'll go through it together. Okay, so fairly straightforward question, like none of the calculations are really difficult, but for part A, we're just deciding whether the acceleration is positive, negative, or 0 for each section. So part A, positive, negative, or 0? Negative. It's going faster in a negative direction. That's a negative acceleration. Okay, part B?
0.
0. Traveling at a constant velocity in part B because the velocity is not changing. Okay, part C? Negative. Part D?
0.
0. Part E?
Positive.
Positive. And F? 0. Okay? All right. So calculate the value of the acceleration where it's not 0. All right, so in part A here, we go from -2 to -4. All right, so our change in velocity is -2, and that happens over 1 second, so 2 meters per second squared, -2 meters per second squared. All right, it's exactly the same in C. Right, so it's the same calculation. In E, we go from -6 to +6. So that's a change in velocity of +12, right? And that happens over 2 seconds. So we're looking at +6 meters per second squared for the acceleration during part E. All right, Now the tricky part. Sorry.
Wait, I don't think I understand that question.
Which one?
What is it? It makes it, because I thought it was 6 minus 2. So where did that go?
For part E?
For the acceleration.
Yeah, for the acceleration, right? So whenever it's not 0. So for part E, it goes, so our, remember, A equals VF minus VI over T. So that's going to be positive 6 minus negative 6. VI was negative 6, right? And that happens between 7 and 9 seconds, which is 2 seconds. Right? So 6 minus negative 6 is like adding, right? Subtracting negatives like adding, so 12 over 2 is positive 6 meters per second squared. With me on that? Okay, where did I lose you?
I thought the initial velocity was 2.
Oh, no, I'm only doing for part E.
Oh, okay.
Remember it said, calculate the value of the acceleration where it is not 0. So here it's negative 2. Here it's negative 2 meters per second. Here it's positive 6 meters per second squared.
Of those 10 and 9.
What was 10?
Right there. Is.
You're right. I misread it. You're right. It goes to 10, so it's over 3 seconds. So it should be 4, positive 4 meters per second squared. Okay, tricky part. Obviously there's something else tricky, but okay, what's the tricky part of this question? Where, or sorry, at what time does the bird change directions?
E.
It happens during E, yes, but at exactly what time?
Oh.
How many seconds?
7.5.
No.
85. 85.
85. Oh, 8.5?
Yeah.
Yes, right there. 8.5 meters per second is the time when the bird changes direction. Okay, here's why. Because most people go with their gut and they go right here. That's when it changes direction. See, because that's when the line starts going up. That's when their acceleration is positive. Are they moving in a forward direction yet? Their velocity is still negative, right? As long as the line is below 0, they're moving backwards. Agreed? It isn't until right here that they start moving forwards, right? So I don't know how a bird does this, but it's going like this and then goes like this, right? I'm assuming it just kind of does a loop and they didn't look at it in a very complex way, right? But this is exactly what throwing something up in the air looks like on a velocity versus time graph. Okay? As soon as it leaves my hand, its acceleration is down. And its acceleration is down the entire flight, but it's only moving down after it reaches its maximum height. Okay? So velocity versus time graph of throwing something up in the air would look like this. Okay? Its initial velocity would be upwards. Let's say it's, I don't know, 4 meters per second. Okay? And then its final velocity would be negative 4 meters per second. And this would occur halfway through the flight. Okay? That would be when it's at its maximum height. How fast is it going at its maximum height? 0. That's exactly what this graph says. What would the slope of this line be? It is negative. I'm actually thinking of a specific number.
Oh, yeah, I'm not
Negative 9.81.
Negative 9.81 meters per second squared. Slope of a line on this graph is acceleration, right? Mind blown here? Okay. See if the pressure is building. It hasn't blown up yet. Okay. All right, so does that sort of make sense? Okay, remember we said that slope equals y minus b over x, and on this graph, that's this. A equals vf minus vi over t. Well, the acceleration of this line, if it was something thrown up in the air, would be 9.81 meters per second squared down. That's what we'd be showing. Making something. Okay, I would like you guys to try this one. I'm just going to make it big enough for you to see. Okay, so. Whoop. Two can play that game. Okay, I want you to do number one. Okay, so I want you to describe the motion, okay, of the object that's being shown on the graph, calculate its total displacement, and then draw what the position versus time graph of that would look like. Okay, that'll make you think. Going from one graph to another type of graph really tries your understanding. Okay, let's have a look at this one. So for the first part here, for A, what's going on in this first part between 0 and like 10 seconds?
It's going at a constant speed.
Right, going at not just a constant speed, but also even more specifically,
Velocity.
yeah, a constant velocity of 5 meters per second forward, okay? We would want to be that specific because we actually get all of that information from the graph. It tells us which direction, forward. We can read the number off the graph, so we want to be that detailed. All right, a physical kind of impossibility occurs along this line here. It instantaneously changes velocity to the exact opposite of what it was doing before. Okay? Nothing instantaneously stops, turns around, and goes the other way. Right? That's what this graph is saying, okay? Because the line is straight down. You don't get a straight vertical line on a graph basically ever if time is involved. Okay? But now it's saying in this part that it's going backwards at a constant velocity of -5 meters per second. Okay? Well, actually, we shouldn't say negative and backwards. We should just say backwards at 5 meters per second. Because negative backwards is forwards. Yeah. You can. So now we're supposed to draw what the position versus time graph of this looks like. So now I have to kind of convert in my mind and say, all right, what does an object traveling forwards at a constant velocity look like? Okay, well, I know that traveling forwards at a constant velocity is an inclined line. It's showing me the position changing by the same amount every second. In this case, 5 meters every second. Okay. Now, in order to know exactly where this line should end up, okay, I know that it's over 10 seconds. Right, so this would stop here at 10 seconds. Time would be on this axis, right? Okay, how do I figure out what position it's at on my position versus time graph from this graph? Can I calculate displacement from this graph? Right, I know it's traveling at 5 meters per second forward for 10 seconds. How far would it go? 50 meters, right? Just d equals v times t, right? So 5 times 10. Right, so that means that this line here would end at positive 50 meters. Now, if it did exactly the opposite thing for the next 8 seconds, is it going to get all the way back? No, it's going to end up how short? How much is a little bit? Well, we don't want to guess. Can we calculate it? Okay, so it's going to go at -5 meters per second for 8 seconds, which means it's going to go 40 meters back. So then I would have a line here at 10 meters and say, all right, here's 18 seconds. Okay, it gets to that point, and at the end, it still has a displacement of 10 meters forwards. It takes a bit of figuring, right? It takes a bit of understanding what each motion looks like on a different graph, right? Not unreasonable for you to be asked to do something like that. And take this graph and convert it to this graph. You know you can calculate all the stuff you need off the first graph in order to build the second. And I'm not saying that's a quick question, but it's not unreasonable for you to be asked that. Yeah. Any other questions on that one? Okay. We already did that one. And we did the snowmobile question. Just go down here where I can't see. All right. You don't have to draw this to scale, right? But I want you to read that question. You're going to have to do a bit of calculating as well, a little bit of v equals d over t. Okay? But what I'm going to want you to do is, with the information in that question, figure out how to draw the two graphs, a velocity versus time graph and a position versus time graph for that particular thing. Okay, so I want you to answer that question, okay, using those graphs. You can use those graphs, okay, and they can help you to answer the question. Right? So I'm going to give you a little bit of time on that one because it's a little bit of work to do there. My recommendation is that you convert the minutes to seconds. How many seconds in 10 minutes? 600, so it's an easy conversion. You may.
Well, at least not all of it.
Rather than have you draw this one up. Okay, so velocity of an automobile changes over an 8-second time period, and we don't even have the table, so we can't even do that one. Forget about that one. Okay, let's talk about tomorrow. Tomorrow you're gonna have a quiz, first off. Okay, it's gonna have some V equals D over T and some graphing on it. Then we're gonna do our first lab. Okay, it'll be on position versus time graphs. It'll be very straightforward. Okay, we'll have your Chromebooks, you'll be able to do everything on Google Sheets and Google Docs. I'll have it all ready for you. Then we'll walk through the lab report process and all of that kind of stuff tomorrow as well. Okay, but if you recall the other day, I asked you make sure you have this app on your phone. At least one member of your group needs to have that app on their phone. Okay, the free version of it, not the one you pay for. Okay, the free version of that on your phone for tomorrow, so that it can communicate with our Bluetooth carts and get all of your measured data. Okay, so I will post the quiz right after school today. Make sure you give it a try tonight. Shouldn't take you more than 5 or 10 minutes. Okay, if you like to do it, okay, or come and do it at lunch tomorrow, whatever. Okay, as long as you have it done before you come into class. Okay, if you have some questions about it, I have supervision all through lunch tomorrow, so I won't be much help, but I'm outside on supervision, so you can hunt me down. Okay, If you walk all the way around more than twice and don't catch me, it's because you're walking in the same direction as me. Turn around and go the other way, and you meet up with me because I just.
Would you be able to redo like the mock quiz, like the time?
Can you redo the mock quiz? Yeah, I guess. I mean, you're just doing it at home. I'm not checking.
Yeah. So can we like redo, like if we want to retry it again, like just do it over and over?
Like the one you're going to write in class?
No, like the one online.
Yeah, it's just a PDF.
Oh, okay.
Yeah, it's not a Google form or anything like that. Yeah, it's just a PDF. Here's 2 questions. Try it.
All right.
Yeah. Okay. Questions on that? All right. So it's going to be kind of a busy day tomorrow. Right? I have 2 things going on.